A company wants to install Norman windows, which are windows in the shape of a rectangle capped by a semicircle. The perimeter of the window, including the segment between the rectangle and the semicircle, is 14 feet. What dimensions will maximize the area of the windows? Okay, so first thing we're going to do is what we try to do with all these, which is start off with a basic sketch, a little bit of information of what this picture looks like. I don't know anything about any of these dimensions at this point, so I'm going to go ahead and label these as Y for this height right here. I'm going to call this X for that length right there. And I know that if this is a semicircle, that we're going to kind of refer back to what we know about area of a circle being pi r squared. So the area of a semicircle would be half of that. And the circumference would be 2 pi r. So the circumference of the semicircle would then be half of that, which would be just pi r. Okay, so if I'm looking at the radius here, from here to here, the radius of that circle, that is r, but it's also in relationship to the x. This tells me that r is equal to half of whatever x is. So this is all information we need as we sort of move towards solving this problem. Okay, so again, what we're trying to do is set up some information for this. So our objective is to see if we can find out how do we maximize the area. So we've got our area here, which is our x, our y, our half of pi r squared. So this is our rectangle, and this would be our semicircle. So we're trying to maximize this. And what we're going to use in order to do that is we've got to try and figure out some information about how to take a derivative of this and plug in some information. So I'm going to look at what I'm going to call one of my possible constraints. And we'll throw them all in here at once. So I know that x has to be greater than 0. I know y has to be greater than 0. And I know that for this particular case, I need to know the perimeter. And the perimeter here is going to be these pieces added up. So I've got 2x, and I've got 2 y's. So I've got the x here, the x here, the y here, and the y here. And then I've got the area for this piece, or the circumference of this piece, which we said was the pi r. So there's all of our pieces that we're going to sort of use for this as we move forward. Let's look at our perimeter. 2x, 2y, plus pi r. I have a lot of letters in here that I don't want to necessarily deal with. So first thing I'm going to do is I'm going to get rid of this r. And the r, if you go back to what we just talked about, we're going to use this idea here. R is the same as half of x. I'm going to start plugging in some information that I know. So perimeter, we know needs to be 14. I have my 2x, my 2y, and my half pi x. And I'm going to just go ahead and try and get one of these letters by itself. In this case, I'm going to try and isolate my y value. So I'm going to go ahead and move some things around. So I'm going to move the 2y by itself, which means if I do that, I have negative 2x, negative 1/2 pi x, and I have 14. Now I'm going to go ahead and divide everything by 2. So here I have negative x, negative 1/4 pi x plus 7. So I now have this sort of known value for y being isolated. I'll come back and deal with that again later. Now we're going to use this piece, though, to plug into our area formula and see if we can use that to find our first derivative. So our area formula, we said, was x, y, that's the area of the rectangle, plus 1/2 pi r squared. In this case is r. We already sort of switched that out earlier to the 1/2 x. We have our x, 1/2 x squared. So I know that my area is x, y, plus this squared multiplied out. It's going to give me 1/8 pi x squared. And there's where, or why we sort of got that y by itself, is so that I can go ahead and isolate it now and plug it in. So I'm going to go ahead and simplify this by saying that the x times my y value, which I said was negative x minus 1/4 pi x plus 7 plus 1/8 pi x squared. So I can go ahead and multiply this out, distribute that x to all these pieces. So I'm really going to sort of distribute this out to each part. And so that now gives me negative x squared minus 1/4 pi x squared plus 7x plus 1/8 pi x squared. All right, so I'm going to take the first derivative. So when I do that, I get negative 2x. This portion right here comes out to be negative 1/2 pi x. This piece here comes out to be positive 7. And then our last piece here comes out to be positive 1/4 pi x. All right, so if I'm trying to minimize or maximize, first thing is I want this to be equal to 0. Next thing I'm looking for is here's an x, here's an x, and here's an x. So I'm going to go ahead and put all those pieces together. So I really have negative 2 minus 1/2 pi plus 1/4 pi all times x, and then plus the 7. All right, so if I move this around a little bit, I'm going to move the 7 to the other side, which now leaves me my negative 2 minus 1/2 pi. And if you want to combine these together, you can. Because I'm using this to solve, I'm just going to leave it for now. I'm going to go ahead and divide both sides. So what I have then is x is equal to negative 7 divided by negative 2 minus 1/2 pi plus 1/4 pi. And I'm going to put that into a calculator and get that x is about 2.108 feet. So I have one of my two dimensions. How do I get the other one? Well, we're going to go back over here. We're going to plug in here now. So this tells me that y is equal to negative 2.108 minus 1/4 pi times 2.108 plus 7, or y is approximately 3.236 feet. And so we now have the dimensions that will maximize my area. And again, if we wanted to prove that this was a maximum, we could take, so if we want to verify that we actually have a maximum, that would mean that our second derivative would have to be less than 0. So if I take my first derivative, which was negative 2x minus 1/2 pi x plus 1/4 pi x plus 7. And I take the second derivative, it's going to give me -2 minus 1/2 pi plus 1/4 pi. That becomes 0. And you can clearly see that's less than 0. And so therefore, this will be a max. All right. Thanks a lot. We'll see you soon.